Welcome back, everyone. We've got a really fascinating explainer for you today. We're literally putting on our cosmic detective hats to unlock the secrets of this mesmerizing stellar structure called Caldwell 78, or NGC 6541 if you prefer catalog names. We're going to use some of the absolute best, most advanced astronomical data available today to solve some ancient mysteries locked deep within this cluster.
So, a bit of background. Caldwell 78 was actually discovered way back in 1826 by the Italian astronomer Niccolò Cacciatore. But here's the crazy thing. Despite knowing it's there for nearly 2 centuries, it is only just now yielding its deepest secrets. The core mystery we're investigating today is how incredibly young-looking stars you could honestly call stellar vampires, manage to hide right in the middle of a chaotic, ancient cluster.
Okay, here's our mission briefing for today. First, we'll meet Caldwell 78, then the UV-BSS hunt, pulsating oddities, chemical fingerprints, a gamma-ray mystery, and finally, the cosmic time capsule. Let's get into it.
Section 1. Meet Caldwell 78, the scene of the crime.
You'll find Caldwell 78 hanging out in the Corona Australis constellation. It's classified as a post-core collapse globular cluster. Imagine an ancient, spherical city of stars, over 13.25 billion years old. Over time, the gravitational tug-of-war between hundreds of thousands of stars caused the heaviest ones to sink right to the center, which triggered a catastrophic collapse inward. It creates this absolutely chaotic bumper car environment where stellar collisions and near misses are, just a regular Tuesday.
And this extreme, collapsed stellar city, it sits at a staggering distance from us, 24,800 light-years away, deep within the inner halo of our Milky Way. At that vast distance, trying to peer into that ultra-dense collapsed core is a massive challenge for astronomers.
Which brings us to Section 2, the UV-BS hunt, finding the fountain of youth. You see, older optical surveys really struggle to find anomalous stars here. When you look in standard visible light, the brilliant, highly evolved red giant stars just completely blind our instruments. Their light bleeds and saturates the image, basically hiding everything in that crowded core. But by using the Hubble Space Telescope to conduct a high-resolution ultraviolet survey, a UV survey, the red giants suddenly become faint and those hot, blue straggler stars light up like beacons. Astronomers use this UV route to successfully pierce that crowded core and manage to identify 94 hidden blue stragglers.
Moving on to Section 3, pulsating stellar oddities, measuring cosmic heartbeats. By monitoring 70 of these centrally located blue stragglers across multiple wavelengths, researchers discovered a handful of variable stars, meaning stars whose brightness actually fluctuates over time. Specifically, they found 9 SX Phoenicis stars, which physically pulsate in size and brightness over very short periods, and 3 W Ursa Majoris stars, which are actually 2 stars orbiting so closely together that they constantly eclipse each other.
Now this right here is essentially an EKG of a star. It's a light curve showing the regular, rhythmic heartbeat of one of those SX Phoenicis stars, labeled SXP1, measured across 3 different light filters. By tracking this super precise pulsation period, which, by the way, is less than 1/10 of a day, astronomers can unlock the star's underlying physical properties.
And it gets better. By taking these pulsation periods and the star's intrinsic luminosity, researchers can calculate their true masses using theoretical models. And what they found is just astonishing. The average mass of these pulsating stars is 1.06 solar masses.
So, why is that astonishing? Well, the math reveals a massive discrepancy. The average mass for a regular star surviving in this 13.25 billion-year-old cluster should only be around 0.75 times the mass of our Sun. But these blue stragglers, they're sitting between 1.0 and 1.2 solar masses. They are literally way too heavy. This proves beyond a shadow of a doubt that they are merged entities. In that chaotic, collapsed core we talked about, smaller stars crash together, or maybe one just siphoned material right off a companion, acting like a stellar vampire, to create a massive, rejuvenated star. Mystery number 1 solved.
All right, Section 4, Ancient Chemical Fingerprints, Seeds of the Inner Halo.
High-resolution spectroscopy gives us a really deep chemical breakdown of the cluster's old red giant stars. First off, Caldwell 78 is highly metal-poor. Its iron content is extremely low compared to our Sun, which completely confirms its ancient status. But check out the elements beyond that. Silicon is surprisingly enhanced, while titanium is depleted. Overall, alpha elements, which are elements built by fusing helium atoms together, are high.
What this tells us is that the massive cloud of gas that originally formed Caldwell 78 was enriched by a very specific cocktail of ancient Type II supernovae from massive progenitor stars, entirely avoiding the later iron-heavy Type Ia supernovae. The cluster also shows enhanced S-process elements, heavy elements that are forged slowly inside intermediate mass stars. So taking this entire chemical signature together, researchers conclude that Caldwell 78 formed incredibly quickly. We are talking about a formation timescale of perhaps just a few 100 million years after star formation first sparked in the galaxy's central regions. It is a pristine, untouched relic of the Milky Way's inner halo.
Section 5. A Gamma-Ray Mystery. The Invisible Glow.
Enter the Fermi-Latz Space Telescope. Astronomers using it detected a marginal gamma-ray emission with a statistical significance of 4.4 sigma coming from right within the tidal boundaries of Caldwell 78. Now, gamma rays are the absolute highest energy form of light in the universe. Finding them in a quiet, dead cluster of ancient stars? Highly suspicious. So what exactly is generating this invisible, high-energy glow?
Well, the answer brings us right back to where we started. Remember that collapsed bumper car core? Let's connect the dots here. Step 1, that insanely high stellar encounter rate forces stars together. Step 2, this creates exotic, close binary systems. Step 3, within these binaries, dead neutron stars get spun up to incredible speeds by stealing matter from their companions, becoming millisecond pulsars. And finally, step 4, these rapidly spinning pulsars act like cosmic lighthouses, emitting the steady stream of gamma rays that the Fermi telescope is detecting.
Section 6. The Cosmic Time Capsule. The final verdict on Caldwell 78.
When you put it all together, this cluster is an absolutely vital time capsule for astronomers. Its extreme post-core collapse environment creates a perfect laboratory for studying stellar dynamics. It acts as a hideout for those massive merged vampire blue stragglers we track down using UV light and heartbeat measurements. Its unique chemical makeup makes it an unpolluted relic of the very early Milky Way inner halo. And, of course, that chaotic density makes it a likely breeding ground for exotic, invisible millisecond pulsars powering a gamma-ray glow. It's really the whole shebang.
Caldwell 78 proves to us that just because something is incredibly old, it doesn't mean it's quiet. Which leaves us with this thought. If a single ancient cluster hovering 24,800 light-years away hides vampire stars and invisible pulsars, what other mind-bending cosmic secrets are lurking right now in the Milky Way's oldest relics? Thanks for joining me on this explainer. Keep looking up, and I'll catch you next time.